Okay, so for the next group of problems, it's going to be important. It's going to be really helpful to you to have your calculator in the right mode. And this is not the normal mode for our graphing calculator. So the first thing you want to do is make sure that you're in polar mode. So if you go down to where you usually highlight function, you want to go over to polar. The other thing that's going to be helpful to you is that under format, so second zoom, instead of rectangular coordinates, rectangular GC, which you usually have highlighted, go over, highlight, and hit enter on polar GC. That's going to give you R and theta only instead of your X and Y's. And that's really going to be helpful to you when you are trying to trace and figure out what's going on with each of your polar coordinate graphs. Okay, so this problem, we want the maximum R value and where those points occur for 2 sine of 3 theta. So 2 sine, 3 theta. When you change to polar coordinates, again, your theta, your variable turns into theta from X, which is nice. I'm going to go ahead and graph. And you can see my graph is way off here. I'm going to go back to zoom. I'm going to do zoom square. Zoom square maybe zoom standard first. Don't know what's going on with there. We go. Zoom standard and then zoom square is going to help out there. Zoom square makes your calculator window into a square. It makes your X distances the same as your Y distances. Instead of a rectangle, I'd like it to be straight. So now if we trace, you can see instead of X and Y, we have R and theta. So if you go out to your furthest distance there, R is 2, theta is 0.5235987. Okay, so our maximum R value is 2, and we could have just analyzed our equation to get that as well. And it's happening 3 places. If you're not sure what that angle is, I would do some guessing and testing. So the nice thing about this, 0.52359. All right, well, looks like pi over 6. Let's test it. Pi over 6. There's your decimal approximation for pi over 6. So our graph here, that first petal that looks like it's in the first quadrant there, is at pi over 6. And then we do have symmetry over the y-axis. So if I have one petal happening at pi over 6, the petal that looks like it's over there in the second quadrant, that's at 5 pi over 6. And the petal that's straight down is at 3 pi over 2. So pi over 6, 5 pi over 6, and 3 pi over 6. Trying to do as little memorization as possible. Just have to know how the equations work. Okay, now we're going to do a lot of writing equations. A couple roses, which is just like the problem we just saw. So a rose with 8 petals and a petal of length 5. So the way our equations work, and you can use either sine or cosine to get a rose curve. So I'll just use cosine for this first one. I'm going to have R equals. If I want a petal length of 5, we can kind of use this last problem for a model. Here, our petals were length 2. So if I want a petal of length 5, 5 is going to be my coefficient. I'm going to use sine for this one. And then you can do a little testing with it. But if you remember, you have a different rule for whether you have an even number of petals or an odd number of petals. If you have an even number of petals, the number in front of your theta times 2 is how many petals you have. So if I want 8 petals, I need a 4 in front of my theta. Now, if you can't remember that, no big deal. Go back to your calculator and test it out. So I'm going to do 5 sine of 4 theta and make sure that I get the graph I want. I should get 8 petals my petals should be length 5, and I can figure out that my petals are length 5 from that trace. Beautiful. So for a rose with 9 petals with petal length 6. Again, I'm not doing y equals here. Careful. If my petal length is 6, 6 is out front, I'm going to do a cosine curve for this one. And then I have to remember here, if I want 9 petals, since 9 is odd, that's the number I want in front of my theta. We don't want 4.5 there. That's not going to give us 9 petals. And then I would, of course, on the test it out. 6 cosine 9. And make sure 1, 2, 3, 4, 5, 6, 7, 8, 9. Got them. And trace out to the end to make sure. Oh, it was already on the end. Yep. Theta is 0, R is 6. All right. So if I'm working with a limestone, I think is the way you say it, a limacone with an inner loop, if my R value is 6, what I need to happen is I need my 2 numbers out front to add to 6. So R equals, for both cardioids and limacones, I have something like this. I have 2 numbers in front that are either subtracted or added. Here, I'm going to do a little guess and test with them, but I know if I want my maximum R value to be 6, my 2 numbers need to add to 6. So I'm going to use 4 and 2. That will also give me that difference of 2 for the loop. If you're not sure which order, and this is the thing that I forget, I can never remember if the 2 needs to come first or the 4 needs to come first. So if I do 4 minus 2 cosine theta, try it out and see if that did not give me a loop. So 2 minus 2. Try the other direction. There I have a loop of length 2. My maximum R value is 6. So we just tested it out and we found I needed 2 and a 4. Here let's go ahead and jump to E and then we'll deal with the cardioid. For the inner loop of length 3, this one doesn't give you any details about what the maximum R value can be. So it can be whatever you want. Now I know from doing part C, I need a difference of 3, and I need my smaller number in front. So to get a difference of 3, I'm just going to do 3 minus 6, and I'll do sine for this one. And of course, we're going to test it out. 3 minus 6, sine of 6. My max R value on this one is 9. That wasn't a detail that we needed, but my loop is 3. The difference between a cardioid and a limacone is that with a cardioid, your 2 values are going to be the same. So instead of having a 2 and a 4 that are subtracted there in front of your cosine or sine, we're going to have the same value. That A and that B value in the equation are equal. So if I want a max value, R value of 8, I don't have any options here. If I'm doing a cardioid, I need 4 and 4. Those 2 have to be the same. And of course, you can check that out on your calculator. All right, very close to the end of the polar coordinate section. One more video for graphing by hand, and then we'll be on to complex numbers.